Okay, applications of differential calculus, page 6. This first problem, there's a example 5, which is a similar problem, which you can look at if you want. Basically, we're going to use this long-lost formula, which we saw a few months ago, which is that the area of any triangle, even if it's not right, is 1/2 AB sine of angle C. And in this triangle we have here, you can see that this is A and this is B, and the theta here is angle big C. And what they're saying is, okay, let's say that this is like two sides with a little hinge, and it's like opening and closing. And they're saying, hey, the triangle formed by these two sides and this hinge, the area is constantly changing when the angle is changing. At what rate does it change? So basically what they're saying is, how does the area change according to the change in the theta or the angle? And so let's make this into a theta. And so like let's figure that out. So first of all, dA d theta would be equal to 1/2 AB. And remember, A and B are constants. They're one of them 6 and one of them 7, and never changes. So you don't have to take the derivative of those. You just use the coefficient rule and leave them sitting out there. Now the derivative of sine theta is cosine theta. And then we don't need to do the chain rule because what's inside is already just theta. Okay? So, and then it asks us, what is the exact rate of change at theta equals 45 degrees? So now we're going to plug in that into here. So 1/2, and A is going to be 6, and B is going to be 7. And cosine theta is going to be cosine of 45 degrees. And so basically that's going to be 21 cosine of 45 degrees. And cosine of 45 degrees is 1 over square root of 2. So it's 21 over square root of 2, which is about equal to 21 divided by square root of 2, 14.8. Is 14.8 like what is it? It says the rate of change in the area of the triangle. It doesn't say what the units are. Oh, there it is, centimeters. So it's going to be centimeters squared per degree, because that's the unit of the angle. Okay. I think. Yeah, I think it is. Okay. Oh, you know what? I did something wrong. Actually, it's per radian. Okay. Now, if we wanted to do degrees, then we would need to put cosine of theta, or it'd be sine of theta divided by sine of theta, and the theta would be like theta, we'd have to convert from degrees to radians, because you know how the derivative of sine is cosine? That's true if the angle's in radians. So if it's in degrees, then what we do is we divide by 360 and we multiply by 2 pi to get radians, right? So then when we do the, when we take the derivative, dA d theta, we actually need to do the, so we have sine, blah, blah, blah. And then we need to take the, chain rule of that. So we multiply by 2 pi times 360. Okay, so here, instead of just having cosine 45, we're also going to have 2 pi times 360. And then here we're going to have 2 pi times 360. And then so instead of 21 square root of 2, we're also going to multiply times 2 pi times 360. And then, so the 14.8 is also times 2 pi divided by 360. Gives us 0.259. Okay, centimeters per, and now we can put centimeters per degree. Okay. 15. The voltage in a circuit is given by V of t equals 340 sine 100 pi t, where t is the time in seconds. At which rate is the voltage changing when t equals 0.01? So, you might not even understand what voltage is, but they gave us a function, so there's no big deal. You say, okay, what rate is voltage changing? It's going to be 340 cosine 100 pi t, and you use the chain rule, so you multiply times 100 pi. Okay, and then let's see. So 340 times 100 pi would be 34000 times pi, 3.14, 106,760. So 106,760 cosine 100 pi t. So it says, what about when t equals 0.01? What happens? So, let's see. I'm going to make sure that I'm in radians mode first. So I go mode. Yes, I'm in radians mode. That's good. So I'm going to put 100 pi, I'm going to put cosine of 100 times pi, and there's a pi button here somewhere. There it is. No, there it is. 100 times pi times t, and the t, it says, is 0.01. Okay, and then we find what that is. Oh, it's -1. And then we multiply that times 106,760, and then it's 106,760. Okay, and that would be volts per second squared. And then what rate is the voltage changing? When V of t is maximum. When V of t is maximum, well, V of t is maximum at, like it's a sine wave, right? So it's maximum at this point here, okay, when sine attains a value of 1, which would be at pi over 2, right? At pi over 2, sine achieves a value of 1, multiplied times 340. So, we already know that the t value, so it would be, when is 100 pi t equal to the maximum value of sine, which would be pi over 2. So it would be, t would be 1 over 200, right? Okay, so now we're going to find out what v dash of t is at 1 over 200. And so that'll be calculated by cosine of pi over 2. And cosine of pi over 2 is 0, right? Cosine of 90 degrees is 0. So this is a trick question. What is the rate that the voltage changing when V of t is maximum? 0. And that kind of makes sense because the voltage is at its peak right here, right? So it's going up and then it's about to go down. So that's why the peak, or that's why the rate of change is 0. All right. 17C, optimization. So we just finished the kinematics part, and now we're working on optimization. Finding the minimum or maximum value of a function is sometimes called the optimal solution. Optimal solution found using the optimization process. 3 ways to find such solutions. Okay, one way is to use derivatives. We can use derivatives to find stationary points, etc., etc. Okay? So derivatives, we would take the first derivative, we would take the second derivative. That's one way. What about a second method? A second method would be to, like remember when we did quadratics? We could find the optimal solution by, like for example, finding the axis of symmetry of the quadratic, because like remember the optimal solution is either the highest or the lowest point, and we could use x equals negative b over 2a to find the optimal point of the parabola, for example. So we could use like axis of symmetry if it's a quadratic axis of symmetry. And then the last option would be the calculator. We could graph it and then use the TI-84, and then we use the function second calc maximum or minimum, and then we can also find the optimal solution. So there's at least those 3 methods. Circle which of the 3 methods are good for finding exact solutions. Okay, so the first 2, derivatives and and the axis of symmetry, find exact solution. Using the calculator doesn't necessarily find the exact solution. Maximum or minimum values happen at stationary points or at the end points of an interval. So remember, we just did a problem a couple problems ago where there were no stationary points. So then we had to test the left and right endpoint to see which one of those was higher. 3 ways to test a stationary point to see if it is a local maximum or minimum. One of the ways, if you only want to take the first derivative, is you could take the first derivative and you could take the first, you can make a sign diagram. And then after you make the sign diagram, like let's say that you found a stationary point there, and then you found the sign diagram plus and minus like that, then you know that this is a maximum, because you can see that like it goes up here and it goes down here, so of course it's a maximum, right? So you could use the first derivative only and the sign diagram. The other thing you could do is you could do the first derivative and then you do the second derivative to confirm concavity. Remember that if you find out that it's concave up, right, or concave down, concave up or concave down, then that kind of tells you if it's a minimum or a maximum. Okay. And last of all, you could graph it. Once you graph it, you could just graph the function f, and then you could see that it's a minimum or maximum. Okay, so those are the 3 methods of checking to see if a stationary point is a local maximum or a local minimum. All right. Last of all, here is a optimization problem solving method, which you should go back to in case you get lost or have difficulty starting on a problem. So first of all, diagrams are very important. If you can draw a diagram, sometimes that helps you understand it. The other is you need to find a formula, and the formula is going to have at least 2 variables. One of the variables is going to be the variable which needs to be optimized, which is going to be like, for example, the area, or the volume, or the cost, or something like that. Okay, and then there's another variable which is like the input, and modifying the input may or may not optimize the output y. Okay, so it's going to be y equals blah 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 x. Okay, and a lot of times what happens is you get one output, and then you have like 2 inputs. So you have like an x, and you have an f, or you have like other things. And what you need to do is you need to make sure that the x and the f are related, and make it only in terms of x and not in terms of x and f. Okay, and we'll see that as we go on here. So step 3, find the first derivative, find the values which make the derivative. So like once you get it in terms of just the output at y and the input x, then you can take the derivative, dy dx, and then you can find out where the stationary points are. And step 4, if you have a domain which is restricted between like points A and B, then you need to check the endpoints also, okay, in case the endpoints are higher or lower than the local maximums and minimums. And then finally, you write your answer in a sentence. Okay? So keep that in mind when you are doing the rest of these pages on optimization.